Example, let f of x equal x plus 1 over x is the example we're about to consider. In the context of the end of chapter 3 and the beginning of chapter 4, which is kind of theoretical stuff. We're going to talk about some theorems, and we're also going to talk about some terminology that we want to start to get used to. I've hinted at these theorems and this terminology before, but we haven't been official about it yet. What does the graph of this look like? Let's just focus on when x is positive. I could graph this when x is negative as well, but I'm going to graph it when x is positive. Let's actually make a rough graph of this without technology by graphing x and 1 over x individually and then imagining adding the graphs. This is a useful thing to be able to do. The graph of y equals x looks about like this. And the graph of y equals 1 over x looks about like this. They happen to cross when x is 1, right? Because when you plug in 1 into there, you get 1. And when you plug into the 1 into there, you get 1 over 1, which is 1. When x is 1, y is 1. That's where they cross. But for the function f, I'm adding these two functions. F of x is x plus 1 over x. That means for each input, I can add the outputs. So for example, when x is 1, the output is going to be 1 plus 1, 2. The point 1, 2 is going to be on the graph of f of x. What does the rest of the graph look like? Again, you have to think graphically. You have to imagine adding these. When x is close to 0, y equals x is close to 0, but y equals 1 over x is large. When you add a number close to 0 with a large number, you get a large number. On the other hand, when x is large, 2, 3, 4, etc., 1 over x is small, but x is large. I'm still going to get a large output when I add a small and a large number. I hope it's intuitive that the graph should look something about like this. Now, is it going to have a minimum at 1? I'm doing a quick mental calculation, and yes, it does have a minimum at 1. I did a quick derivative in my head there. That's what the graph of f of x looks like. Can we confirm with calculus that that was what the graph of f of x looks like? Yes, we can. How? Take the derivative. This can be written as x plus x to the negative 1. Take the derivative. Find f prime of x. The derivative of x is 1. And the derivative of x to the negative 1, we did this already today, is negative 1 x to the negative 2. So I get minus x to the negative 2 here, which is the same as 1 minus 1 over x squared, which, if you like, you can subtract these fractions by getting a common denominator of x squared. This is the same as x squared minus 1 over x squared. Any of those formulas is fine for f prime of x. What would it take to use calculus to confirm that f of x is decreasing when x is between 0 and 1 and increasing when x is bigger than 1? It would take me understanding what the graph of this function is. And where is it positive and where is it negative? In particular, I don't actually have to graph this. I just have to figure out where it's positive and where it's negative. That can be done first by figuring out where it equals 0. If I set this equal to 0 and solve for x, I get what are called the critical points of the function, of the original function f. New terminology. Critical point. If I set the derivative equal to 0, you may want to write this down. If you set the derivative equal to 0 and solve for x, what you're finding are called critical points. In this example, if I focus on this equation here, the only way this fraction can be 0 is if the top is 0. Now, the bottom is 0 when x is 0, but then the function's undefined, so we don't think about that. We can focus on just the top. which can be easily solved for x, either by factoring or by doing this. And taking the plus or minus square root of 1 to get plus or minus 1. The critical points are plus or minus 1. You also can find that by factoring. This factors as x minus 1 times x plus 1. This is not the derivative here. It's the numerator of the derivative in this form. That's what it is. But it equals 0 at the same places where the derivative equals 0. So my critical points are 1 and negative 1. These are the critical points of the original function f. What do I do with them?
Why is it not x to the negative 1, 2?
Because I use this form of the equation. And I focused on the top. That's why. You should get the same answer if you use this form. If you set this equal to 0, or this, and solve for x, you would really get the same equation to solve for x. X squared would be 1, so x would be plus or minus 1. Same answer. Again, what do you do with these critical points? Well, let's just focus on the positive one. That's what I wanted to do up here. I could think about negative values of x as well. I'm just not bothering. Let's focus on the positive critical point. You make a number line. 0 is where f is undefined. So that's not a critical point here because the function is not even defined there. But I want to draw it on the graph here for scale or for perspective anyway. 1 is a critical point. Think about numbers between 0 and 1 and bigger than 1. And think about, based on those numbers, whether f prime is positive or negative. Do you have to pick a particular number? No, you actually don't have to. You can. Between 0 and 1, I could pick, for example, 1/2. Imagine plugging 1/2 into the derivative. What would you get? You can plug it into any of these formulas. It's a little tricky. It might be best to think about this factored form here. If you plug in 1/2 into that factored form for the numerator, you get a negative number. Because 1/2 minus 1 is negative and 1/2 plus 1 is positive. A negative times a positive is negative. And in this formula for the derivative, the bottom is not negative. When you plug in 1/2, you get a negative divided by a positive, it's negative. F prime is less than 0 in this interval for all values of x in the interval. I didn't put the x in there, I could have. On the other hand, if x is bigger than 1, you'll get a positive output for the derivative. Both of these numbers will be positive. You're dividing by a positive number. The derivative would be positive. What do we know derivatives tell us about the original function? Where derivatives are negative, the original function is decreasing. Slopes are negative. Where the derivative is positive, the original function is increasing. I could add this kind of thing to my diagram. F is decreasing in here and increasing in here. This arrow pointing downward means decreasing. This arrow pointing upward means increasing. That's a way you may confirm that the graph goes down when x is between 0 and 1 and up when x is bigger than 1. And therefore, at this point, it's got to be a low point of the graph, a minimum. What I'm doing there in saying what I said verbally and showing this kind of work is I'm using something called the first derivative test. First derivative test. These types of problems are the kinds of problems you find in section 4.1, what I just did. And I'm not assigning yet. First derivative test. There's also a second derivative test. The second derivative test can also be used to confirm that this critical point is a minimum by confirming the second derivative is positive when x is positive. Actually, it's good enough for the second derivative at the one point to be positive as long as the second derivative is nice, continuous. But we will confirm the second derivative is always positive when x is positive here because we can go ahead and take the second derivative. Probably easiest to differentiate this thing. If f prime of x is 1 minus x to the negative 2, differentiate that to get f double prime of x, the derivative of 1 is 0. I bring down the negative 2, subtract 1 from the exponent, and simplify. I get positive 2 x to the negative 3. Same as positive 2 over x to the positive 3. The exponent's negative, but the expression itself is positive. It's a negative exponent when you write it that way. But because of what negative exponents mean, it means this. And when x is positive, that's positive. It's positive when x is positive. And that fact is essentially saying by something called the second derivative test that there is again a minimum at 1. The graph has a horizontal tangent right there. X equals 1 is a critical point. F prime of 1 is 0. And F double prime is positive near 1. So the graph's concave up. It's got to be a low point as opposed to a high point. Does that make intuitive sense? Again, I haven't officially shown you the statements of the first derivative test or the second derivative test. I've just described them. Let me describe them again. Listen really carefully. Don't write anything down. Just listen really carefully. How do you confirm a point in a graph happens to be a minimum with the first derivative test? You take the first derivative and you find where the derivative is 0, which we did, plus or minus 1. Those are called critical points. We focus just on the plus 1. I could look at the negative 1 as well, I'm just not. That's where the derivative is 0, so the tangent line has to be horizontal. The tangent line approximation near that point would have a 0 slope. The first derivative test confirms what you see visually here, that the graph decreases, then increases as you pass through that critical point. So it's got to be a low point. I take the first derivative and I think about on these intervals, where is it positive and where is it negative, by imagining plugging numbers into the first derivative. I just imagine that you could literally plug numbers in if you wanted to and compute the value of f prime. You would get a negative number when the inputs are between 0 and 1, and you get a positive number when the inputs are bigger than 1. That means the function's decreasing over here, then increasing over there, as we saw here. That's an official confirmation that that is a low point. The second derivative test confirms the same thing. And by the way, you don't have to use both tests in general. You should be able to use either test, but one test is good enough to prove you got a minimum or a maximum. In this case, the second derivative is this, and that's positive when x is positive. Graphically, that means the graph is concave up. And so if a critical point is where the tangent line is a slope of 0, and the graph otherwise is concave up, it's got to be a low point, a minimum. When would you get a maximum? When the graph looks like that, which it doesn't for this example. What would happen is that your derivative to the left of the critical point would be positive and to the right would be negative, and the graph would be increasing and then decreasing. With the second derivative test, your second derivative would be negative, the graph is concave down. Now, again, that's all content of 4.1. What about 3.9? That's about theorems. And the most important theorem in section 3.9, or 3.10, excuse me, is called the mean value theorem. Let's take the time to write that down. It says, suppose you've got a function f that is continuous on a closed interval. I've used this notation at least once before. That's the closed interval from A to B. It's the set of numbers between A and B, including the endpoints. and differentiable on the open interval from A to B. That's an open interval. It's unfortunate that the notation for open intervals is the same as the notation for points. You have to tell if you're talking about a point or an interval based on context. This is an interval. A and B are numbers on the number line. A is less than B. This set is every number between A and B, including A and B. This set is every number between A and B, excluding A and B. You'd make open circles at A and B. You might wonder why continuous in the closed and why differentiable in the open. The reason is because we can get away with these assumptions. Function might be continuous and differentiable on a bigger interval, but we're trying to write down minimal assumptions to guarantee the conclusion. And the conclusion is then there is a number, call it C, in the interval from A to B, such that f prime of C equals f of B minus f of A divided by B minus A. The derivative is the slope of a tangent line. This kind of expression is also a slope. It's a slope of a secant line. What's a secant line? It's a line connecting 2 points on the curve, not necessarily tangent to the curve, usually not tangent. If you draw a generic graph, say of a concave down function, this theorem makes perfect sense if you think about it carefully. Let's pretend this is A and this is B. It's a nice continuous and differentiable function. The theorem says, in this situation, we know there's some number C between A and B where the slope of the tangent equals the slope of the secant. The secant line is this line right here. There's your secant line. Secant line of slope, rise over run, f of B minus f of A divided by B minus A. F of A is right here, and f of B is right here. It's just an average rate of change. If this is a position graph, that's average speed. Average velocity if you were including back and forth motion. The tangent line at some value C is parallel to this. That's what this equation says. It's got the same slope. Where is that tangent line? Maybe right about here. I'm trying to eyeball it. And the value C would be right about there. Question? Was there a question over here? I saw a hand. Okay. So the theorem, when you think about it graphically like this, seems perfectly reasonable. Actually proving it is very difficult. Proving it from scratch. Only assuming you know basic facts about real numbers, for example. Why is it difficult? Well, you first have to develop your theory of defining what continuity means and what differentiability means. We have done that in this class, though we haven't done it really in a rigorous way. Once you've defined those things, it's still difficult to prove this, even though it seems reasonable. There are functions that this does not apply to, functions that are not continuous or not differentiable. You should take the time to look at examples in the book or maybe my extra video where I talk about such examples. But let's just illustrate this theorem. Back for our example. Let's go ahead and use the example we were looking at just 10 minutes ago. F of x equals x plus 1 over x. I need to pick an interval here. Let's say A is 1 and B is 2. According to the theorem, on the interval from 1 to 2, if the function is continuous, which it is, and if I consider the interval from the open interval from A to B, on which the function is differentiable, which it is, because this function is continuous and differentiable if x is strictly positive. I can say there's a number C between 1 and 2 where this equation is true. Let's see if we can find it. This stuff implies f of b minus f of a over b minus a is f of 2 minus f of 1 divided by 2 minus 1. Plug in 2 into this, you get 2 plus 1/2, you get 2.5. Plug in 1, you get 2. This simplifies to 0.5 or 1/2 with that slope of that secant. I'm going to need the derivative, f prime of x. I already found that, it's this. I can go ahead and replace x with c and write this. And to find c, I want to set this equal to the slope of the secant line, 1/2. And solve for c. Can it be done? Yeah, or maybe I'll write this as c squared minus 1 over c squared. And then I'll cross multiply. Might be the easiest way to do this. So I'm looking at these being equal and cross multiplying. So I get 2 times c squared minus 1 equals c squared times 1. Simplify. Looks like c squared is 2. So c, if I want it to be between 1 and 2, must be the positive square root of 2, which is about 1.4. I don't want to take the negative square root because that's not between 1 and 2. So here we were able to solve for c. Visually, what's going on is, again, the graph of f looks like this. It's the graph we already drew. There's 1, 2, excuse me. Here's the purple graph that I drew. When x is 2, the output's 2.5. The secant line in question is this secant line. The c we found that to be square root of 2, which would be right around here. The tangent line is parallel to the secant line. Now you might say, give me 1 minute here. You might say, who cares? That's a good question. Who cares? Here's why you should care. The mean value theorem is necessary for proving other important facts, like the fact that if the derivative is positive over some interval, the function is increasing over that interval. Or if the derivative is negative over some interval, it's decreasing over the interval. You also can use the mean value theorem to prove the first derivative test, which we're going to use a lot in chapter 4. So it's a fundamental fact, this mean value theorem. My extra video I talk about at the beginning of the video, I believe, places where you cannot use the mean value theorem, where the conclusion fails. That'll come up on the homework. And I think I also do maybe an application or two in the video.